Okay, new section as far as I'm concerned, although we're still in the same section of our book, 3.3. We've already learned a ton of information in 3.3, and we're not quite done, but we're getting pretty close. There's two more derivative rules that I want to add to this kind of big list that we're accumulating. One's called the product rule, and one's called the quotient rule. And that's what we'll be going over in this section. Before we get to these new rules, maybe a quick recap of the rules that currently exist would help. I kind of think about them in groups. So, sort of the first group is what you might refer to as the polynomial rules. And that starts with this power rule that tells you how to take the derivative of something like, I don't know, x to the third power. All you do is you bring the exponent down in front, so 3 times. And then you raise x up to a new exponent, one less than the old one. So 3 times x squared would be the derivative of x cubed. Next one we learned is what's called the coefficient rule. And the way to think about that one is, we know how to take the derivative of x cubed as demonstrated above, but what if it was 5x cubed? Well, no big deal. Informally speaking, you pull that constant multiple of 5 out in front, and then just multiply that by whatever you get when you take the derivative of x cubed. You wouldn't be done here, you'd still have to take the derivative of x cubed, but that would involve the power rule, not the coefficient rule. So for the sake of demonstrating the coefficient rule, I'll leave it right here. And then the third one, the last of the major polynomial rules, is this idea of sums and differences. And what that says is, yeah, now you could take the derivative of 5x cubed, for example, and you could already take the derivative of x to the fourth power, for example. But how do you take the derivative of the sum of those two things? Well, good news, all you have to do is take the derivative of the first thing and add to it the derivative of the second thing. In other words, the derivative of a sum, what's written on this line, is the sum of the derivatives, these guys right here. And in my head, when I'm thinking about the polynomial rules, I'm really just thinking about these first three. But I guess technically, to make this as complete as possible, I have to include a couple more little facts. The fact that a derivative of the variable, the derivative of x itself, is just 1, and the derivative of a constant, not to be confused with this coefficient rule, tells you the derivative of a constant is just 0. And with all these different rules, which again I like to call the polynomial rules, we can take the derivative of any polynomial. So I don't know, 3x cubed minus 5x squared plus 11x minus 10, sure. But the good news is these rules don't just allow us to take the derivative of any polynomial, they're useful in a lot of other settings also. This sum and difference rule works when we're taking the derivative of the sum of any two functions, not just power functions like we see with polynomials. Same with the coefficient rule. Also, as we learned in the last section, the power rule doesn't just apply when n is a positive whole number. If n is negative, so maybe you're thinking rational functions, or n is fractional, so you're thinking radical functions, we can still apply the power rule. So that's all kind of cool. If I were writing your textbook, I probably would have ended 3.3 right here. Been like, that's a ton of rules. That's plenty for a student to digest in one section. We'll learn everything else in the next section. But your book didn't. Your book was like, well, as long as we're learning the rules, let's throw a bunch of rules at them. So there's more. The way I categorize these, the next group in my head, involves exponential and logarithmic functions. The exponential rule tells you the derivative of b to the x equals b to the x times the natural log of b. The only comment that I have here is b is the constant. So this works on things like the derivative of 2 to the x power. So don't confuse that with the derivative of x to the 2 power, which is something you would figure out using the power rule. When the base is a constant and the exponent is your variable, you don't use the power rule, you use the exponential rule. And the nice thing about the exponential rule is it says this derivative is almost just 2 to the x. Wouldn't that be great if you could just kind of drop the derivative symbol? It's not quite that, but it's pretty close. All you got to remember is to tack on some constant. The constant in this case is the natural log of 2. More generally, the constant is always the natural log of the base. And you'll run into instances in this class where we're asked to take the derivative of 2 to the x power, but what will be far more common is when you're asked to take the derivative of e to the x. More often than not, when you're using the exponential rule, playing the role of the b will be the number e, 2.71 something. And the reason why is because e serves as a really nice base, so this function, e to the x, ends up being really useful. And the great thing about taking the derivative of this function is the derivative of e to the x is just e to the x. So in that special case, loosely speaking, you can just drop the derivative symbols. And there's a parallel down here with logarithmic rules. If somebody asked you to take the derivative of, I don't know, the log base 2 of x, for example, you could do that using this rule. You'd say it's almost just 1 over x, but not quite 1 over x. I have to tack on this natural log of 2 down in the denominator here. And this question will arise in our class, but again, far more common will be when you're using logarithms, the base will be e. And you don't write the log base e of x, you write the natural log of x to signify that the base is e. And for the same reason that this simplifies so nicely, that the natural log of e is just 1, this simplifies really nicely. When you run into the derivative natural log of x, you get for your derivative just 1 over x. And much like e to the x will be the most common case of using the exponential rule, the natural log of x will be the most common case using the logarithmic rule. One more group in my mind of functions are these trig functions. And this is a group that we're going to add on to in the next section. But for now, the only two trig functions we know how to take the derivative of are sine and cosine. And those two functions almost serve as each other's derivatives, but not quite. The derivative of sine is cosine. Unfortunately, the derivative of cosine is not sine, it's negative sine. You just have to remember that negative in there. Anyways, those are all the rules that we've developed so far in 3.3. I think of most of them as building blocks, meaning we're going to learn the derivatives of lots of different functions like sine or cosine or log base 2 or e to the x, constants, variables, power functions using the power rule. We're going to learn all these kind of simple building block functions, and then we're going to learn how to kind of put them together using rules like the coefficient rule and the sum and difference rule. So it would look kind of weird, but if I asked you to take the derivative of, I don't know, e to the x minus 2 times sine of x, you could figure that out. And maybe the way you think about this is I kind of have these two building blocks, e to the x and sine of x. And I know both of their derivatives. Here's the derivative of sine of x, and here's the derivative of e to the x. But it's not enough to just know the derivatives of the building blocks. You have to know how to put those together. I'm not just asking for the derivative of e to the x, and then later asking you for the derivative of sine of x. I'm asking you for the derivative of this function, which involves both of those building blocks. Fortunately, those building blocks are put together in a way that we know how to deal with. Using the sum rule and the coefficient rule, I can rewrite this question like this, and now all I need to do is figure out the derivatives of those different building blocks. And you're like, great, so we know how to put building blocks together. Well, kind of. We know how to take the derivative when the building blocks are put together in this fashion, but what if they're not put together in this fashion? Namely, what if they're multiplied together? Right? What if somebody asked you to figure out the derivative of 2e to the x times sine of x, for example? You would not be able to figure out this derivative because the building blocks, the e to the x and the sine of x, are being multiplied together, and we don't have a derivative product rule yet. What we're going to learn in this section is how to take derivatives like this. We've already seen instances like this. Like, for example, I asked you to figure out the derivative of x to the 5th times the square root of x. And I made the big point that it's not just 5x to the 4th times 1/2 x to the negative 1/2. The derivative of this times the derivative of this. And I proved that to you by rewriting this question using some algebraic rules and showing what the answer should be. I said that you could rewrite this as the derivative of x to the 5th times x to the 1/2 power. And then algebra, not calculus, tells you that x to the 5th times x to the 1/2 power is x to the 11/2 power. Because you think about this as 10/2 and this is 1/2, and you add up those exponents. And now that it's no longer written as a product like it was up here, we could take the derivative using the product rule. 11/2 x to the 9/2 power. Cool. But what if you were in an instance where you couldn't use algebra to rewrite this so that it was no longer a product? What if, for example, I asked you to find the derivative of x squared times the natural log of x? There's no way algebraically to rewrite this so that it becomes something that we can take the derivative of. We're going to need the derivative product rule. Fortunately, it's the very next thing in my notes. Here's the derivative product rule. It's kind of a mess when you just look at it, especially if you write it in its standard notation. But what it's telling you is that the derivative of the product of two functions, think building blocks, is equal to the derivative of the first function times the second function. Note, we're not taking the derivative of g of x here. It's the derivative of f of x, and then after you figure that out, multiply it by g of x itself, not g of x's derivative. And then add to that the derivative of g of x multiplied by f of x itself. Again, not its derivative. Well, this is the standard way to write this. A much more user-friendly way to write this statement is what you see right below here. F and g are assumed to be functions. This is saying the derivative of the product of f and g is f prime g plus g prime f. If you can tie together the blue box and the green box, you're picking up the notation really well. And maybe if you're the inquisitive sort, you'd wonder why that works. Why is the derivative of a product equal to this weird-looking expression? Well, as we often do in this class, we could go back to the difference quotient and kind of prove this, although it's a little bit tricky to do it. The way to think about it is, if we had this function p of x, maybe p for product, and it's equal to f of x times g of x, and we wanted to know the derivative of p of x, we'd say it's the limit as h approaches 0 of p of x plus h minus p of x divided by h. And again, since p of x is f of x times g of x, instead of writing p of x plus h, I could write f of x plus h times g of x plus h. If p of x is f of x times g of x, p of x plus h is f of x plus h times g of x plus h. From that, I have to subtract p of x, which, as we see written right here, is just f of x times g of x. And then I have to divide that whole thing by h. How am I going to simplify this to get this into a form that looks like one of my derivatives so I can come up with a general rule? Well, there's this trick. We want to subtract and then add this expression to the numerator. So the first comment is, as long as we subtract it and add it, we're not changing anything, right? We're essentially adding 0 to the numerator. So the expression that's written up here will be the same as the expression that's written right here once I add and subtract in that new term. It'll make the algebra work out nicer if I subtract it first. So I got minus f of x plus h times g of x here, and then add it next, f of x plus h times g of x. First comment, why did you do that? This gets into something that you'll see a lot in proof classes. Often you don't know why you're doing that. When you're learning how to prove things, often a big challenge is not being able to come up with the proof on your own, but just being able to follow the steps if somebody else writes it. So if you wouldn't have thought to go from this line to this line, you are not alone. There's no reason anyone would think to go from this line to this line. But maybe you just trust that the process works out. You're like, yeah, I see that you could do that. I don't know why you would, but I see that you could. And as strange as it feels when you're kind of getting comfortable with proofs, that's all you want to do. What we're going to do next is recognize that we can think about the numerator as a sum of two things. All this stuff plus all this stuff. And when you have a fraction where the numerator is a sum, you can break it up into two different fractions. You can think about it as f of x plus h times g of x plus h minus f of x plus h times g of x divided by h plus f of x plus h g of x minus f of x g of x. Essentially, this parenthesis went here and this parenthesis went here. And since I have the common denominator, if I were adding these guys up, I'd add up their numerators and write it over h a single time. What I'm saying is this whole expression is equal to what we have down on this line. So really I have the limit as h approaches 0 of all this stuff, but referring back to limit laws, that topic that I glazed over many videos ago, one of the laws tells you that if you're taking the limit of something plus something, you can change that to the limit of the first thing plus the limit of the second thing. Doesn't look like we're getting anywhere, but we're actually really close to the final answer. The final step before we evaluate the limits is to recognize that up here in the numerator, it's hard to see the minus sign, but we're subtracting these guys. Each of the terms have an f of x plus h in them. So I can factor out this f of x plus h and this f of x plus h and pull that out in front of my fraction. Similarly, over here, both of the terms have a g of x in them. So I can take that g of x and pull it out in front of my fraction. And now a really nice thing happens. Over here I have the limit as h approaches 0 of something times something. And my limit laws, again, tell me that that's the limit of the first thing times the limit of the second thing. And the limit of this first thing is something that I can figure out. The limit as h approaches 0 of f of x plus h. Well, if h gets really close to 0, this becomes x plus 0, in other words, x. What I'm saying is the limit as h approaches 0 of f of x plus h is just the function f of x. The limit as h approaches 0 of this mess over here is exactly what we would get if we used our difference quotient with the function g of x. Remember, our difference quotient gives us the derivative, so this entire term right here represents g prime of x. If it helps to see where all the pieces are going, this turns into this when I evaluate the limit, and this turns into this when I evaluate the limit. So I got f of x times g prime of x, and then I have my plus sign, and then I evaluate the limit over here, and the same thing happens. The limit as h approaches 0 of g of x. There's no h's here, so nothing happens when I let the h's go to 0. It's just g of x. And then the limit as h approaches 0 of this mess. This mess is exactly what you'd get if you use the difference quotient on the function f of x, so this is f prime of x. Some arrows to help you track the pieces. This turns into this, and this turns into this. What we're left with, if you write the terms in a slightly different order, is f prime times g plus g prime times f. Did you follow that? If you did, that's really good. If you can follow this level of a proof at this point in your mathematical journey, that's really impressive. It's not something that's required for our class, but it's the kind of thing that'll help you in future classes and the kind of thing that I'm supposed to kind of introduce you to in this class. So if you followed that, great. If you're like, I could follow your work, but I never would have thought to do these steps, perfect. That's still beyond where you should be in our class. And if you can't follow this at all, you're like, too many letters, I just don't get it, the colors didn't help, I'm lost. Frankly, that's not that big of a deal. It's something I'm supposed to introduce you to, but it's not something I'd ever test you on. Now you've seen it. It's worth pointing out that you can also prove this kind of with a picture, prove it geometrically. The idea here is we can think about the product of two things as the area that you'd get if you made a rectangle and one of the edges was one of the thing and a perpendicular edge was the other thing. So what I'm saying is if g of x represents this length and f of x represents this length, the area here is one way you can interpret what f of x times g of x means. Right, if you're in a room and the length of one of the walls is 10 feet and another wall is 8 feet, you got an 80 square foot room. And then we can kind of think about the derivative as the rate of change, so how quickly this thing is changing. So like maybe at some instant f of x is this long and an instant later it's a little bit longer. Same idea with g of x, at one instant it's this long and an instant later it's this long. Well, then at the first instant the area is this big, but an instant later the area is this big. And so if we think about how much the rectangle is changed by, you might be able to talk yourself into this being f prime times g, and this being g prime times f, and this being so arbitrarily small that it just goes to 0. It's not the most rigorous proof in the world, but it's kind of a cool way to think about where the product rule comes from. If you're wondering why I didn't do it more carefully, it's because I know that there's a video out there that I'm going to link on our wall map page that does it way better with animation. It's really cool. It's one of those 3 blue, 1 brown videos. So I guess what I'm saying is I'm going to leave this proof with the picture for that video. That's a lot of talking, a lot of derivation, a lot of theory stuff I'm supposed to show you, but we haven't done any examples. You haven't really seen anything that looks like something you'd be tested on. Something that you'd be tested on is answering a question like this. What's the derivative of 2e to the x times sine of x? A common theme in calculus is, when you see a new problem, don't forget stuff you've already learned. What this is 2 times something. This 2 is a coefficient. So I can pull that 2 out in front and say that my answer is 2 times the derivative of e to the x times sine of x. Now, if we think about f of x as the first function e to the x and g of x as the second function sine of x, and recognize that f prime of x is e to the x and g prime of x is cosine of x, we have all the pieces that we need to use our product rule, because our product rule tells us that the derivative of a product is the derivative of the first thing, f prime of x, which is this e to the x, times the second thing, which is sine of x, plus the derivative of the second thing, which is g prime of x, which is cosine of x, times the first thing, which is this e to the x power. Be careful with the parentheses. The product rule creates 2 different terms. It creates a plus sign, and if you don't write the parentheses, the 2 will only hit the first half of it, not the entire thing. You might notice that I left some room in between. I did that intentionally. I think for a lot of students, you'll quickly go from this line to this line, but it's not a horrible idea to really detail your steps of how you got from here down to here. It's not really necessary in this example, but I think what you'll see in harder examples, it'll be nice to do things this way. So let me write an in-between step here. I still have my 2, and then I'm going to open up some big parentheses. I'm taking the derivative of something times something. The way I do that is I take the derivative of the first thing, so the derivative of e to the x, and then I multiply that by the second thing, the sine of x. But then I'm not done. I have to add to that the derivative of the second thing, the derivative of sine of x, multiplied by the first thing, the e to the x. We did all this work kind of off to the side, which allowed us to go from this line to this line, but putting this line in between can be really useful. Make sure that you understand what this is saying. The work that is still left to be done in the second line is represented by the d over dx symbols. So this is saying we still need to take the derivative of e to the x, and this is saying we still need to take the derivative of sine of x. The factors that don't have a d over dx in front of them, for example, sine of x, e to the x, and I guess this 2 as well, are done. We don't have to do any calculus there. So the purple stuff is done. The, I don't know what color stuff this is not done. We do that extra work to go down to this final line here. Not sure if you followed all that. Let's do a couple of examples, then we'll end this video. The first one, find the derivative of x squared natural log of x. What I'd encourage you to do for this problem is write the intermediate step. I'm going to use the product rule here, which means I have to take the derivative of the first thing, x squared, multiply that by the second thing, the natural log of x, add to that the derivative of the second thing, the derivative of natural log of x, times the first thing, x squared. Now I look at this line and think about d over dx as signifying work still needs to be done. The derivative of x squared, using my power rule, is 2 times x. I need to multiply that by the natural log of x. Not the derivative natural log of x, just the natural log of x. To that I want to add the derivative of natural log of x, which is just 1 over x. Maybe you're thinking 1 over x times the natural log of e, but the natural log of e is just 1, so the derivative of natural log of x simplifies really nicely. That's this derivative part, but I'm still not done. I have to multiply that by x squared. I don't have the d over dx symbol written anymore, so in a sense I'm done, although there's no reason not to simplify this. I think this is a perfectly good answer for our class, but I'm always going to simplify these because the steps that I do when I simplify these gives you practice rewriting expressions. And you want to be able to rewrite expressions, not so much for the answers, but more for the questions. Being able to manipulate things algebraically makes your calculus life so much easier, especially when these problems get harder in the second half of this class. So how could I simplify this? Well, there's not a whole lot I'd do with the first term. Just leave that as 2x natural log of x. But the second term I can simplify. 1 over x times x squared. Think 1 over x times x squared over 1. So 1 times x squared divided by x times 1. In other words, x squared over x. If I have an x squared on the top and an x on the bottom, I can cancel one of the x's up top with the x on the bottom, and I'm left with just an x. This is a great answer, and I don't even know if we can simplify it any more than that, but we could rewrite it a little bit differently. We could recognize that this x and this x can be factored out in front. So an alternative way to write this is x times 2 natural log of x plus 1. I don't know that either one of these are simpler than the other forms. I just want to make the point that either one is equivalent. Any of these three are correct final answers, although I'm slightly biased and kind of like these two a little bit more than this one because this one can be simplified. It's worth pointing out that we were just asked to figure out the derivative of this x squared natural log of x. But there's different calculus questions we could have been asked. For example, we could have been told that there's this function x squared natural log of x, and we want to know the slope of the tangent line to this curve at the point where x equals 1. Or we might be asked, what is the rate of change of this function when x equals 1? Or we might be asked, evaluate f prime of 1. All of those things are the exact same. What you do for those is essentially the work that we have up above. F of x is x squared natural log of x. The work I did in purple tells me that f prime of x is 2x natural log of x plus x if I choose this top form. And if I know f prime of x, figuring out f prime of 1 is easy. Just copy exactly what you see here, changing all the x's into 1s. So I have 2 times 1, in other words 2, times the natural log of 1 plus 1. You probably don't remember the natural log of 1, but I bet you learned it in a pre-calculus class. It's equal to 0 because the natural log of 1 is asking you the question, what power do you have to raise e up to change it into 1? And since e to the 0 power equals 1, the natural log of 1 equals 0. So this is 2 times 0 plus 1, in other words 0 plus 1, in other words 1. This isn't meant to be any new knowledge, just kind of reminding you of some stuff that you already learned. A couple more examples. We've seen this problem before. This was a problem in one of the many videos in my last section of videos. The derivative of x squared plus 1 squared. In the past, we said, well, we don't know how to take the derivative of something times itself. So what we have to do is expand this and take the derivative of 4x squared plus 4x plus 1. Rewriting this expression this way made it conducive to our old rules. But now that we have new rules, we don't have to do that. We could say that this question is asking us, what's the derivative of 2x plus 1 times 2x plus 1? Because what it means to square something is multiply it by itself. It's no longer necessary to expand these binomials to get it into this form. Just use the product rule. Think about this 2x plus 1 as f, and this 2x plus 1 as g. If you really want to show all your steps, take the derivative of the first 2x plus 1, and then multiply that by the second 2x plus 1. Add to that product the derivative of the second 2x plus 1 times the first 2x plus 1. What's the derivative of 2x plus 1? Well, if you really want to go overboard and show your steps, I guess you could say, using the sum rule, it's the derivative of 2x plus the derivative of 1. Using the coefficient rule, it's 2 times the derivative of x plus the derivative of 1. And then I know the derivative of x is just 1, and the derivative of any constant is 0. So I get 2 times 1 plus 0. 2 plus 0, I get 2. If you're really showing your steps, I guess you could do all this work. But I bet we're at the point in the class where you can just look at this and be like, derivative of 2x plus 1, that's just equal to 2. I don't think it's necessary to show any work in between this line and the line before. This derivative of 2x plus 1 turns into this 2. This 2x plus 1 goes right here. Then we have the derivative of this 2x plus 1, which creates this 2. And then this 2x plus 1 goes right here, in case the arrows help you. This is technically the correct answer, but I probably wouldn't leave it this way. I'd either be like, I have 2 of these things plus 2 more of these things, so I have 4 of these things. Or what I think would be a little bit more common for students to do is get rid of all the parentheses by distributing the 2's through. So I get 4x plus 2 over on this side and another 4x plus 2 over on this side. And when I combine like terms, I get 8x plus 4. Note that this 8x plus 4 is the same as the 8x plus 4 you'd get if you distributed the 4 over here. The word simplify is kind of subjective. I don't know which one is more simplified, but I think this and this are two beautiful looking answers. It's worth pointing out it's the same answer that you got using the old methods, and you could argue that it's harder than using the old methods, but that's only because the product here was so easy. What if instead of 2x plus 1 squared, it was some 5th degree polynomial squared? You probably wouldn't want to expand it all out and do things the old way. That algebra would be really tedious. But since we're good taking the derivative of any polynomial, doing it the new way would be really easy. One last example before I end this video. I know it's a little bit long. Sorry about that. Is that if you saw an example like this, the derivative of 3x to the 5th power, you do not need the product rule at all. Right? This 3 is a coefficient. So I can just pull it out in front and say that this is 3 times the derivative of x to the 5th power. And when things are written this way, maybe you see the power rule here. The derivative of x to the 5th is just 5x to the 4th. So I'm done. I get 15x to the 4th as my answer without ever using the product rule. You certainly do not need the product rule here. However, I do want to make the observation that the answer that you would get if you use the product rule is consistent with the answer that you get this way. It's just more work that's unnecessary. If you thought about this as a product of two things, as a 3 times an x to the 5th power, you could say this is the derivative of the 3 times the x to the 5th power plus the derivative of the x to the 5th power times the 3. But note that because this is a constant, the derivative of any constant is 0. So I get 0 times whatever I have here, x to the 5th in this case, but it doesn't matter because 0 times anything is 0. So what this ends up being is just this 3 times the derivative of x to the 5th power. 5x to the 4th times 3. In other words, 0 plus 15x to the 4th. You get the same answer, but maybe more important than seeing that you get the same answer is seeing that because anytime I have a constant, using the product rule with that constant as my function is going to produce a 0 over on this side. So all I'll be left with is this side. And this side is our coefficient rule. Right? It's just written in the opposite order. When you have a constant like a 3, you can pull it out in front of the derivative symbol and then multiply that by the derivative of the x to the 5th power. That's exactly what we're doing here. You could argue that I never needed to teach you the coefficient rule at all, although I doubt there's anyone that's like, yeah, I wish I didn't know that coefficient rule. I wish I just always did things the purple way instead of this really easy pink way. The point here is that you can use the product rule even in some instances where you don't need to use the product rule. But don't worry, even if you use the product rule unnecessarily, it won't give you the wrong answer. It's just extra work for no reason.